Hello, I'm tackling question 1 for group 1. So I'm doing the part 3. The part 3 which is describing how a Bézier curve against a screen rectangle can be clipped. So in this is the Python code in which I'm going to show you how I was able to clip a Bézier curve in a Bézier curve for against a screen rectangle. So first, before we go through the code, first you need to understand there are two main concepts, the mathematical concepts in which you need to know, which are being applied here. So the key mathematical concept using this code, there is the interpolation, then there is the this Castle-Lau algorithm for Bézier curve subdivisions. So the linear interpolation function is based on the formula. So LERP, which represents linear interpolation, P1 t is equals to 1 minus t multiplied by point PO plus t multiplied by P1. So this formula calculates a point between PO and P1 based on the parameter t, where t is a value between 0 and 1. Then there is this one, the Castle-Lau algorithm. So this one is the split Bézier curve recursive function, which implements the Castle-Lau algorithm to split a Bézier curve into smaller segments. It uses the linear interpolation to calculate the intermediate control points. Then this algorithm also involves several linear interpolations, and it is a recursive process. So just to mention, there is also the bounding box calculation, there is length segment clipping, and there is the curve subdivision. So to go back to our code, so all those I've mentioned the two main one and the three additional one mathematical concepts are going to be implemented in this code. So at the top here, you can see we are importing matplotlib.pyplot splt. Matplotlib.pyplot, this one is going to be our visualization library, in which it is going to assist us to display how we have been able to clip the Bézier curve. Then now I'm coming to the linear interpolation into bracket LERP function. So this one, it has three parameters. There is PO, P1 and T. Then the function is supposed to calculate the linear interpolation between points P0 and P1 based on parameter T. So this is now the formula based on this formula. This is now the code representation, 1 minus t multiplied by P0 plus t multiplied by P1. Then we go to, then afterwards, as you can see, we go to the split Bézier curve function. The split Bézier curve function, it has three parameters, P0, P1, P2, P3 up to and P2. So this one is, so these are 5 parameters. So this split Bézier curve function, this function, it recursively splits a Bézier curve defined by 4 control points, P0, P1, P2 and P3 into smaller segments. It uses the Castle-Lau algorithm to perform the subdivision. The function then calculates the intermediate points Q0, calculate the intermediate points Q0, Q1, Q2, R0, R1 and B to split the curve into left and right halves. This process is then repeated until the curve is divided into small segments. So as you can see, so this one we are calculating the intermediate points for curve subdivision using the Castillo algorithm. This one, these are the intermediate points. Then we are recursively splitting into left and right halves. Then remember, this one we are also using conditional statements. If t is equals to 0, we are returning p0. Then if t is equals to 1, we are returning p3. Else, we are now calculating the intermediate points. So remember, parameter t should be a value between 0 and 1. So for this else part, it is representing the values which are between 0 and 1. But now for this one, t is equals to 0 is equals to p, then you return p0. This one is definite points for if it is 0, or if it is 1, then it is given the value. But for the intermediate points in between 0 and 1, you use now this one, the Castellau's algorithm, as you are finding the intermediate points. So the algorithm is this one which I was explaining here. The split Bézier curve recursive function, which is now splitting the Bézier curve into smaller segments. Then in between it is using the interpolation. Yes, interpolation. It uses linear interpolation to calculate the intermediate control points. Then afterwards, now we are coming to the clip segment function. So we have a new function. It is called def. So define clip line segment p start, p end, x min, y min, x max, and y max. So it has one. So it has seven parameters. So these 7 parameters. So this function for clipping the line, this function is defined by 2 points. It has the p start and p end. Then it is run against a screen rectangle defined by x min, y min, x max, and y max. Then it checks for various conditions to determine if the segment is entirely inside, entirely outside, or entirely inside, or partially inside the rectangle. It calculates the intersection points if there is a partial intersection. So remember, there is p start and p end. So this one is the line. So this is the line which it is defining by the 2 points. So and then so line segment defined by 2 points, p start and p end. So this is the p start for the line, and now the p end. And now this x min, y min, x max, y max represent the values of a rectangle. Because just as you know, a rectangle is rectangular such that there is the minimum point, which is now the bottommost, and the y minimum, all those points to form a rectangle. Then we are performing conditional statements. So these conditional statements, so we have if x min is less than or equal to p start 0, then x max and y min is less than p start 1, then afterwards, after all this, we are going to return p start, p end. So this based on this condition, this means that both points are inside the rectangle. Then else if p end for point 0 and x min, or p start point 0 x min, then all these conditional statement, then we are returning an empty. So this one means that both points are outside the rectangle. So then we have now the else condition. So this one is calculating the intersection points if there is a partial intersection. So if there is a partial intersection, this means that the points are partially outside and partially inside the rectangle. Then we have to evaluate this portion of the segment inside the rectangle. Then we are going to clip the Bézier curve function. So as to clip the Bézier curve function, we have this function. This function is called clip Bézier curve. Clip Bézier curve. So clip Bézier curve is defined by 4 control points. We have P0, P1, P2, and P3. These ones are the main control points up to here. Then we have the control points. Then we against a screen rectangle defined by x min, y min, x max, and y max. So it first checks. So this algorithm will first check if the bounding box of the curve is entirely outside the rectangle. If so, it will return an empty list. Otherwise, it subdivides the curve into smaller segments using the function split Bézier curve. Then using the function split Bézier curve, and then it clips the segment against the rectangle using the clip segment function. So as you can see here, we are now defining the points. So remember, this clip Bézier curve, the main function of it is checking if the bounding box of the curve is entirely outside the rectangle. So we are checking this if it is entirely outside the rectangle. So we have bounding box. So if it is entirely outside the rectangle, we are returning an empty list. So here it is. So it is entirely outside. So we are returning an empty list. So here we are saying no intersection since the curve is entirely outside the rectangle. Then otherwise we are going to subdivide the curve into smaller segments using now this function. So otherwise we are now splitting. So this is step size for curve subdivision. So then we are going to split the curve into smaller segments. We are using the Castellao algorithm. Then we are going to clip each segment against the rectangle using the clip segment function. So clip segment function is here. So this is now the clipped segments. So we are initializing an empty list. So for each segment in segments, we are clipping each against the screen rectangle based if now this in this case if it is inside or outside the rectangle. Now we are cutting it into small segments, then we are clipping them if it is outside. Then finally we are at the plotting point. So in this plotting point, for this code, we are defining the starting point the control point 1, control point 2, and end point. Then we are defining the screen rectangle. Screen rectangle will have these values 150, 150, 450. Then so the code will defines the these control points are the one which we had indicated above. There is P0, P1, P2, and P3. So there is P0, P1, P2. So P0, P1, P2, P3, and this one. So this one. So this one are just the same parameters which will be called by the arguments of the above code. So the start point. So for clip Bézier curve, so it calls the clip Bézier curve function to obtain the clipped segment and uses matplotlib to plot both the original Bézier curve and the resulting clipped segment. So in order to show the PL plot, we have the clipped Bézier curve. So remember, this one is calling the clip Bézier curve function. The clip Bézier curve function is this one. It has this one P0. So these arguments, these are the arguments. These arguments are now represented by these parameters. So now it is going to do that function. Then afterwards, after it has finished, so we are plotting the original curve and the clipped elements. Then we are setting the plot limits and labels and everything we are using now the PLT. Remember, PLT is coming from the matplotlib. So then afterwards, after setting up the plot limits, label, and then labeling. So just to finish up on the last part for creating the plot. So we have the PLT function we have already set the plot limits and labels, and also the title and everything. So we are now in this final stage, which now is to show. So remember, this PLT is the one which we had imported here from PyPlot and then given it a nickname as PLT. So PLT, now we are going to use it to now display the plot. So just to show you, let's run. Yes, so now this is now the final visualization, matplotlib visualization. So for clipping a Bézier curve against a screen rectangle. Now this one is now the original curve which has now been clipped inside a screen rectangle. So this is now the y. We have the y coordinate, then the x coordinate. So finally we have successfully clipped a Bézier curve against a screen rectangle. Thank you.